When we start putting the electrons into the orbitals, we need to follow three rules. They are the Pauli exclusion principle, the Aufbau principle, and Hund's rule. Luckily, they're relatively intuitive, so that's great. Just a note, you are going to need to know these and be able to apply them, so make sure you do that. So let's go over them. The Pauli exclusion principle says that no two electrons can have the same four quantum numbers. We said that they can live in the same house, right? But it's got to be a duplex, and we have to have one spinning clockwise and this other spinning counterclockwise. So they can have three of four same quantum numbers, but m sub s must be different, plus 1/2 and minus 1/2. So if they have the same orbital, they can have 3 out of 4 the same. That we can see. At any time, an orbital can be unoccupied, contain one electron, or contain two electrons, but those must have opposite spin. Aufbau says we fill them in order of increasing energy. So we fill them in order of increasing energy. 1s, 2s, 2p, 3s, 3p, that's a p, and a 3 mixed together. I'm not sure what that is. But then here comes something weird. 4s, then 3d. These are really close in energy, so we start to see some things happen there. But we're going to go through something called the diagonal rule, and although it's not always correct when we get to the middle into the larger elements, it's a good rule to at least start with. It's always a place to start, but as long as you know it's not 100% all the time, and if you're going to start doing more in the inorganic, or actually in any of this Gen Chem type stuff, if you're going to go further in chemistry, that there will be exceptions for sure. Now, what affects the energy of an orbital? So we have these ones that we draw straight across, the p's. Why did I draw those? Those are called degenerate orbitals. They're not bad, it means they're the same energy. So they go straight across because they're the same energy. What affects it? Well, size. Size affects it most, and then to a lesser extent, the shape. So size, then shape. Electrons are always going to be in the lowest energy orbits, their ground state, whenever possible. So they're going to, and we're going to fill electrons from lowest energy to highest energy. Ground state, again, lowest energy. Excited state, higher energy. Remember how I said this is going to be repetitive? Yep. Okay. So electron configurations are going to be ground state electron configurations. This is one example of an electron energy diagram, an orbital diagram. But this is where, okay, everything seems intuitive until we get here. 4s comes before 3d, then 4p, 5s, and 4d. So we're going to see some hiccups when we get to the d orbitals. The d orbitals are going to be the row number -1, and the f orbitals are going to be the row number -2, and we'll see what that means in just a moment. Hund's rule. Okay, I'm just going to read it to you for a second. The most stable arrangement of electrons is the one in which the number of electrons with the same spin is maximized. Great. What does that mean? It means when I have degenerate orbitals like this 2p, when I put electrons in them, I have a choice. I could put them up, I could put them down, I could mix it. But Hund's rule says, no, we don't mix it. Hund's rule says they're more stable when they're all facing the same direction. Now they can be all up or all down, but no matter what we do, they all have to be facing the same direction before we come back and pair them. Also, every orbital gets one electron before we pair them. And why is that? Because no matter what, electrons are the same charge, they're both negative. They don't really want to be near each other, but they're going to tolerate each other. But in order to tolerate each other, they're going to require something called pairing energy. So it does take some energy to keep these electrons next to each other. Now, I like to call this the city bus rule. You're going to have to know it as Hund's rule, though, sorry. But the city bus rule, if you're riding the city bus and there's somebody sitting, yep, those are my people. Look at my people. They have heads. There's somebody sitting here and here. Where are you going to sit? Are you going to sit here? Hey, dude, I don't know you. You kind of smell. Let's see, he's giving off an odor. Nope. You're going to sit here in your own orbital, your own seat, because it's way nicer to sit by yourself than to somebody you don't know who smells bad, right? So in the city bus, we get on, we get our own seat whenever there is one possible, and then if we have to, we're going to sit next to somebody else. So Hund's rule is a lot like riding the bus. We get our own orbital, and then once we have to, we're going to pair. This is the shorthand notation that we're going to be writing in eventually, called the condensed notation. You've seen it before, you just haven't explained what it is. This number, the large number out front, is the principal quantum number n. This is L, our angular momentum quantum number, and this tells me the number of electrons in an orbital, but only when it's s, but it's actually in a subshell. Now, if I was specific and said, px, then it would be orbital, but most of the time it's going to be a subshell. So it would just say 2p6. That's a subshell. Even s, we can consider it a subshell, but there is only one orbital, so it's kind of hard to, go out on the limb there. Hund's rule, I want to see how we can do. So let's do a couple of practice. Hund's rules up here says, the most stable arrangement is to have everybody get their own orbital before we pair them. And then we pair them if we have to, and we have all the spins facing the same direction. So you know what I do? When I go to put electrons in orbitals, I'll just put them one at a time, all facing the same direction every time, and that is how I avoid making mistakes in that area. All right, so for example, carbon has 6 electrons. Now, I normally do face this up as far as the energy is concerned. It's a little bit harder to do this in this thing, so we're just going to say that we know that this is less energy than this one, and this is less energy than this one, and these are all the same energy. Okay, so hopefully you can remember that. Now, 6 electrons, we're just going to put them in one at a time and pair them when we have to. 1, 2, 3, 4, 5, 6. So the shorthand for this would be 1s2, 2s2, 2p2. I'm not sure why that just happened. Let's try again. I can always write it if I need to. Okay, I'll just write it. Darn electronics, 1s2, 2s2, 2p2. So that's our condensed electron configuration. Let's try nitrogen. Nitrogen has 7 electrons. So we just count. 1, 2, 3, 4, 5, 6, 7. So this whole Hund's rule thing really only applies to degenerate orbitals. Because remember, this one is less energy than this one, and these are less energy than those. So according to Aufbau, we have to completely fill those before we can move on. Also, you're seeing a full barbed arrow here. Normally we would see a half a barb and a half a barb, but I couldn't find that in PowerPoint. I might be able to make it now that I can write on my screen, so maybe we'll try that. So that gives us of course I wrote in the one place where I'm writing, the electron configuration 1s2, 2s2, 2p3. Now boron, how many electrons does boron have? I want you to look at the periodic table and pause this if you need to. How many electrons does boron have? 5. How did I know that? It's the atomic number. So I didn't give you a charge. There's no charge. It's not an ion. So if it's not an ion, then it's just neutral. It means the protons and neutrons have to be, the protons and electrons have to be equal. Some things are just coming out of my mouth today. All right, so here is our orbital diagram. Fill in the 5 electrons, 1, 2, 3, 4, 5, and we end up with electron configuration of 1s2, 2s2, 2p1. Next up is oxygen. I want you to pause it and try it. Pause it. So oxygen has how many electrons? 8, correct. So we put up our boxes. This is the orbital box notation. So then we just fill 1, 2, 3, 4, 5, 6, 7, 8. So we would have 1s, 2, 2s, 2, 2p, 1, 2, 3, 4. Good. I hope you did well. So we said the order gets a little wonky when we get after the 3s. This is called the diagonal rule. How do you draw it? Well, you have to be able to know some things about the periodic table in order to draw it. So mostly, where do we start the orbitals? So when I go to draw it myself, I start with 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Then you start, every time you start a new row, so 2, you're going to get 2p, and then just fill all the p's in, 3p, 4p, 5p, 6p, and 7p. And then with number 3, you start with d, 4d, 5d, 6d, 7d. Now notice they don't have 7d in here. It doesn't matter. You can put it. It won't affect you at all. 4f, 5f, 6f, and 7f. And you'll notice, again, 6 and 7f aren't there. Don't worry about it. Then the only thing you have to really be able to tell on the periodic table is that you fill 2p before you fill 3s. And then you'll know which way to draw your arrows. Because back in high school, when I learned how to do this, I could draw this all day long, but I forgot which way to draw my arrows. And right here, if you draw your arrow this way or this way, it's correct. This way or this way, it's correct. And honestly, I didn't have it intuitively then. It didn't make any sense to me, really. I was just following a rule. Well, if you're doing that, make sure you're following the rule correctly. 2p comes before 3p. That means the arrow must come this way. And when we do that, we put our arrow in, and then we can follow this through the entire time, and we can fill in that order. I will not give this to you. It's going to be something you'll have to be able to draw on your own, but it does work, and it will give you the right answer. Now remember, there are exceptions. So electrons reside in the lowest available possible energy levels. This is Aufbau. Each orbital can accommodate a maximum of 2 electrons. This is actually Pauli, because if you have more than 2 electrons, they're going to repel each other out of the orbital, but then you would have 2 electrons that have the same 4 quantum numbers. Electrons will not pair, Hund. They are going to take an empty orbital with its available with the same spin maximized. So orbitals will fill in this order, this here, according to the diagonal rule for the most part, and in general, that's fine for this class. This is what the periodic table looks like with where the groups, so you can see that 4s and then 3d. What makes it a little difficult is actually this here comes in here. So 6s, then 4f, then 5d, then 6p. This is when the diagonal rule comes in really handy. So if we want to see that put into the periodic table, I'll show you in just a second. It's actually the next slide, I think. If you remember, I think I did this with you in class. I call this slide, I'm still Jenny from the block. We have the S block, we have the P block, we have the D block, and the F block. So when we get lost or confused, remember helium technically should be here for electron configuration purposes. This is 2 elements wide, meaning it can have a total of 2 electrons and 1 orbital. 6 wide means 6 electrons total divided by 2. equals 3 orbitals. 10 wide means 10 electrons divided by 2 equals 5 orbitals. And this is 14 wide divided by 2 is 7 orbitals. So 14 electrons total. And obviously this is a very old periodic table that I've done this on. This is the order that you fill them in. 1s, 2s, if you want to remember that, you definitely can. You start with hydrogen and you fill on up until you get to the element you want. It is a very redundant system, which we're going to get to. But this is what it looks like with the F block in there. So you can see the F electrons go there before the D. Again, there are lots of exceptions. Terminology that you need to know. A shell is going to be those that have the same N value. A subshell or a sublevel has the same N and L value. And superscripts, you're going to put the total for the degenerate orbitals, the total for the sublevel, up as a superscript. Make sure it's a superscript. And you do not need to put commas. Oh, please, God, stop with the commas. Please don't put the commas between there. So there's no commas needed. You just write a 1s2, 2s2, 2p6, and so on and so forth, okay? So we don't need any commas. I would like to do a couple with you and have you try. I guarantee I'm going to ask you if you know where the F block goes. So be prepared to answer something that has an F orbital involved. So I'm going to do fluorine, and I will do mercury with you. And then I want you to try the rest. I want you to, draw your diagonal rule if you need it. I'm not going to draw, I don't need it, but draw your diagonal rule if you need it, and then we will move on. So fluorine has how many electrons? Get your periodic table out. You're going to see that fluorine is number 9, so it has 9 electrons, and they are 1s. We're not to 9 yet, so that's got to be 2. Then we go to 2s, lithium and beryllium, s2, and then we go to 2p. Boron, carbon, nitrogen, oxygen, fluorine is the 5th one over. So 2p, 5. 5 plus 2 is 7, plus 2 is 9. So that's 9 electrons total. We're supposed to have 9. That is the electron configuration. Mercury. Mercury has how many electrons? 80. One thing I like to do is I like to figure out where I'm going to stop first. So if I'm looking at 80 electrons, it's in row 1, 2, 3, 4, 5, 6, starting with cesium. So I'm going to have 6s, 4f, 5d. I'm going to end in 5d10. Let's just go back a second. Actually, you know what? I'm going to pull up this little slide sorter thing so I can see. How did I know I was going to end up in 5d10? One, two, three, 4, 5, 6. So this is 6s. This is 4f that goes here. Then 5d, 5d1, 5d2, 5d3, 4, 5, 6, 7, 8, 9, and 10. So I'm going to end in 5d10. That's how I know that. Back to my slide sorter, I'm just going to show you back at our diagonal rule. I can even do it on the slide. It doesn't really matter where I do mercury at. 80 electrons. 1s2, 2s2, 2p6, 3s2. I come around and go to here. 3p6. Am I to 80 yet? Nope, because that's going to end in a 5d. So 3p, now I go to 4s2. Then I go from 4s to 3d, 3d10, 4p, 6. Everything's full, so I can just keep going. 5s, 2. From 5s, I go to 4d, 4d10, 4d10, 5p6. I'm still nowhere near 6s, so I can keep going and filling everything. 6s2. Now, 6s, 4f, 14, and 5d is where I'm ending. So 5d, 10, and I'm out. But I should go back, and count to make sure. So 10, 20, 30, that's 30 electrons. 6 plus 4 is 10, so that's 40, plus another 10 is 50. And if you'll believe me, that's 56, 57, 58, 59, 60, 66, 68, I missed this one, 70, 76, 78, 80 electrons. So 2 checks. Make sure you ended where you should have ended, 5d10, and make sure that you end with the number of electrons that you should have had, 80. That number of electrons won't change unless you have an ion. So I'm going to go back to the slide that we were just on, and I want you to pause it and try the rest of them. I am obviously going to give you the answers so that you can check yourself, but this is what you should end up with for those answers. Ask questions, practice, practice, practice. If you're finding different results, if you look them up on the internet, I will explain that to you if you have questions about it, but it's because of energy differences that you're coming up with a different answer. Now, theirs are probably more accurate, but we're going to fill according to the diagonal rule again, because I'm not going to have you know every exception. I'm going to have you know 2 exceptions in the end. So electron configurations are very redundant. We're writing the same thing over and over and over again. You probably realize that. So we actually have a shorthand way of writing things known as the noble gas configuration, or that's usually what they're known as, noble gas configurations. So this is the ground state electron configuration for potassium. Potassium has 19 electrons. It's in row 1. It's in, group 1, row 4. So it ends in 4s1. I should have known that by looking at that, but I said the wrong thing. Sorry. So if I go back to the previous P6, in most cases, helium is the exception. It would be the previous S2, 1s2. All right, so anything past neon, you're going to go to the previous P6. Okay, so when you do that, that is a noble gas configuration. And in this case, this is 3p6. So I go down, helium, neon. This is argon, because argon ends in 3p6. So that is the configuration for argon. I'm going to write argon in square brackets. You must have it in square brackets. Yes, you must. And then I write anything that comes after it. Well, all that comes after it, so it's for 18 of my 19 electrons. So all I need is that 4s1 to complete my noble gas configuration. So it's a lot shorter, but I'm going to have to know that you know how to do all of them. So I will be asking you, so you're going to need to know what I'm asking you. I'll ask for the complete configuration if I want the whole thing. I'll ask for the noble gas configuration if I want the noble gas. And we have a couple more to learn yet. I want you to try these: arsenic, silicon, sodium, and tin. So go ahead and try these, pause it and try it, and we'll go over them. Now you're going to notice in the answers I wrote the whole complete electron configuration for each of these, but I want to go back. So look, this is argon and then 4s2, but let's go back and see how we can do this without having to write out the whole configuration, because that kind of defeats the purpose of using a noble gas configuration if you've got to draw the whole thing out anyway. Let's go back to our diagonal rule. Oh shoot, what was our first one? Was it arsenic? All right, arsenic, silicon, sodium, and tin. Arsenic, sodium, silicon, and tin. Okay, so arsenic is number 33. If I go back to the previous P6, it's argon. So argon ends in 3p6. So I can find 3p6 on my diagonal rule. I can put argon in brackets. I know that accounts for 18 of the 33 electrons I need. I can also find arsenic on the periodic tables, and I go, oh, that's in 4p3. So I should be ending in 4p and the third one. So I can fill 4s, 2, 3d10, 4p, 3. So I have 15 electrons plus 18 electrons gives me 33 electrons for arsenic, and that is correct. So that would be the noble gas configuration for arsenic. I can do that for all of them. I'm going to do it for tin just to show you. So tin is number 50. If I look at my wrong button again. Sorry. If I look at my diagonal rule here, where am I starting? 50 electrons for tin. My previous P6 is, so I go backwards from 50 would be krypton, which is number 36, and it ends in 1, 2, 3, 4. It's in the fourth row, so it's 4p6. So I'm going to go here to 4p, and I'm going to start it with krypton. So krypton, then I fill 5s. Well, where am I going actually? Tin is 5p2. So 5s, I wrote, my mind's in too many different places right now. 5s2, 4d10, 5p2. This is 14 electrons plus the 8, how many? 36? 36 electrons from krypton gives me 50 electrons. So that is a good check. And I end in 5p2, which is also my second check. So you can use the diagonal rule. You don't have to continue to write out the entire electron configuration to then use the shorthand because, again, that defeats the purpose. So here's the answers to the others that you have. Silicon is neon 3s2 3p6, and our other one was sodium. It would be neon 3s1. Again, anything before neon, so hydrogen, not hydrogen, hydrogen doesn't have a noble gas configuration. Lithium through fluorine would be helium, and it wouldn't be a p6, it'd be the s2, would be helium. Is this too good to be true? Yes, but I've been warning you the whole time that this isn't going to be true all the time. There are two exceptions I do want you to know, and they are going to be D4 and D10. D4 and D9. Let's see, D10. So when we're in the D block and we see copper, which ends in D9, and chromium, which end in D4 normally, they are going to make an exception. So if you saw that energy diagram, I'll pull it back up for a sec, it's in your notes. We go back to that energy diagram here. You see that 4s and 3d are relatively close to each other in energy. And what's going to happen is if we're going to try to put 2 electrons in here before putting electrons up here, sometimes it's actually closer and easier in energy. It's cheaper for energy-wise to put those electrons up here first and not have to put another electron into there. So when is this too good to be true? Where is my slide? So when pairing energy is greater than the energy required to move an electron to the next higher orbital. So what's happening here is you'll see that normally this would be 4s2. So argon is what we would predict it to be, 4s2 3d9. And we would predict this one to be argon 4s2 3d4. But what happened is they took one of the s electrons and promoted them up to the d orbitals. So it results in a slightly greater stability because generally filled and half-filled D subshells are going to be more stable. So I'm actually filling an entire shell here when I fill off that 3 shell than when I have them in the 4th energy. So instead of having n equals 4, I now can be filling the n equals 3. Now, most of these exceptions are going to be when Z is greater than 40. You're going to actually see this happen a lot because the energy levels become closer together, and having to transfer an electron between the subshells is going to lower the total energy. So we do see that. And so it's greater stability due to energy and being more stable. Okay, I don't know what I just said, but the stability will be greater because the energy will be lower. So valence electrons, what is a valence electron? I mentioned it earlier, but the valence electron is the outermost shell of electrons. Why do elements that are in the same chemical group act like families, act the same? Because they have the same number of valence electrons. So their reactivity is going to be very similar. They're going to behave similarly. How many valence electrons do we have? Well, this is where our English system does something correct for once, the American system, I should say. Group 1A has 1 valence electrons, 2A, 2, 3A, 4A, 5A. So using the A system, AB system, which is what we use, groups 1 through 8 have the number of valence electrons for whatever their group number is. 6 is 6, 7 is 7, and 8 is 8. So you can just look at the group number and say, oh, that's in group 7, it has 7 valence electrons. We don't really, this does not hold true for, I'll say, non-main group elements, and that's not one word, but oh well. So we're only talking about groups 1 through 8A right now. So arsenic, we look at the highest N value. So you're looking for the highest N value, and that would be 4s and 4p3, 4s2 and 4p3. So if we look at this, the valence electron configuration for arsenic would be 4s2, 4p3. And if I look at arsenic on the periodic table, it's in group 5, so it has 5 valence electrons. I want you to pause this and write the valence electron configurations for silicon, magnesium, phosphorus, and let's pick one. Let's pick nickel, just because. Okay, so pause it, try it. Silicon is in group 4, has 4 valence electrons. The highest N value is 3. Magnesium, 3s2, 2 valence electrons. It's in group 2. All right, and then we had phosphorus. Phosphorus is 3s2, 3p3, and it's in group 5. So it makes sense. Now I said, let's do nickel. Nickel is number 28. It has the electron configuration. Well, let's look what comes first. It'll be argon. Argon 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8. So how many valence electrons does nickel have? 2. In fact, the whole D block has 2, except the D4 and D9s, where they promoted one of their S ones up to the D, because we're only looking at the highest N value here, which is R4S. The atomic radius, this is one of our trends. We talked about Z effective. Well, we'll talk about how these are related. Z effective is going to be kind of the cause of a lot of our trends, or the reason behind it. So the atomic radius is the distance between the nuclei of adjacent atoms. So we can see the nuclei, so we measure the distance between the two nuclei and divide by 2. Metallic radius is the same thing, but with metals. So we just take the distance between these two, I don't know why it's doing that to me, these two nuclei, and we divide by 2. Covalent is just half the distance between covalent compounds. It's exactly the same, we just have a different type of element. Oh, I want to go back. What do you think is going to happen to the size as we go from left to right across the periodic table and from top to bottom? I want you to think about this. This one's counterintuitive to what most people think. So this is written as increasing. So as we go from helium to hydrogen, or from right to left, it increases. And as we go from top to bottom, it increases. So atomic, it's a lot of words for just something like this, something simple. Increases left and down, decreases up and to the right. But wait, neon has a mass of 20.2 grams per mole, and it has 10 electrons, when lithium only has a mass of 6.94 and 3 electrons. What is going on? How can neon possibly be smaller than lithium? Well, as we go from left to right across the periodic table, the Z effective is increasing. But the electrons are the same distance from the nucleus. Did you ever play with magnets? What matters with magnets? Size and distance. So I know you guys didn't see a lot of the old cartoons, but if you got a refrigerator magnet that can barely hold up a piece of paper, if I'm holding one and my daughter's holding one across the room, we'll never know it. But if I get that big old Acme magnet, you know, that the Roadrunner and the Coyote used to use to torture each other, I'm pretty sure that one of us is going to know the other one's holding a magnet. You know what I'm saying? So big old electron magnet here, something like that, we're going to notice that we're holding a magnet. So size of the magnet and the distance. If we're holding a refrigerator magnet right next to each other, they're going to attract each other and we'll notice. So distance matters and size matters. Well, when we go across a period, so as we go across the period from left to right, the distance stays the same, but the size of the magnet increases. So from left to right, distance is the same, but the size of the magnet increases. Now, why am I using magnets? Because we're talking about charged particles. We have a positive nucleus and a negative electron. So the size of the magnet increases, so it's actually going to decrease the size. There's going to be a stronger pull, a stronger attraction to the center, and it's going to constrict the size of the element of the atom. So let's try, use your periodic table, pause this, and tell me a range in increasing atomic radius. That means from smallest to largest for those that are just tuning in. But phosphorus, sulfur, and oxygen in order of increasing. Pause it. So O is smaller than S, which is smaller than P. So phosphorus is the furthest to the left and down, and that is why it is the largest. Try again, pause it, try it, see what you get. You should get fluorine is smaller than selenium, which is smaller than germanium. I'm having a rough go today. All right, so fluorine is the top right, number 9. Selenium coming down, number 34, is 2 steps down and 1 to the left. And same 2 steps down, but 2 more steps to the left is germanium. So we'll see that one being the largest. So go through this, circle which one is smaller, potassium or sodium, which one is smaller, neon or lithium, which is larger, cesium or calcium, and which is larger, potassium or bromine. Pause it and try it. All right, so sodium is smaller because it is above potassium. Which is smaller, neon or lithium? Well, we just talked about that one, neon. Which is larger, cesium or calcium? Cesium. And which is larger, potassium or bromine? Potassium. So this is the one that's counterintuitive. This one is just, yeah, of course, as you go down, it's definitely becoming larger. We're adding in shells. We're going to a larger N value. Those ones are going to be larger. But this, as we go across the periodic table, definitely confuses people. So we're going to have to think about that one and understand why it's happening and what's going on. So unfortunately, these trends are not consistent for the transition elements, so I'll only be asking you about main group elements 1A through 8A for these trends, okay? See you next chapter.